Hey there, Gregory Carlson here with the Calculus Building. So what are the derivatives actually used for? I mean, when am I ever going to use this stuff? Well, let me show you the first use of derivatives. I'm going to put it up here. Let's say we have some function that's telling us the position of something. Okay? So let's say we have a function that's telling us the position of an airplane, or the position of a space shuttle, or the position of some economic value that's moving, or some business value. If we take the derivative of that function, which I'm going to represent by just putting this in parentheses, I'm putting a prime right there. If we take the derivative of that, it tells us the velocity. So let's stick with our space shuttle example. If we have a function that's describing the position of the space shuttle, and we take its derivative, we're going to get the instantaneous rate of change of that space shuttle at every moment in time, thanks to our derivative function. Now we can also take the derivative of this. And if we take the derivative of the velocity function, then we know how the velocity is changing. Okay, how the velocity is changing at every moment in time, which is another name for acceleration. So if we take the derivative of the position function, we get the space shuttle's velocity. And if we take the derivative of the velocity equation, we get the acceleration, because we're getting how the velocity is changing with respect to time. Either you're going faster or you're getting slower. So we'll look at that in more detail later. So let's look at some applications. This first one is, if a rock is dropped near the surface of a certain planet, then its position in the downward direction only, with respect to the point from which it was dropped, is given by this equation, where S of t is in meters and t is the time in seconds. Okay, so we've dropped this, and the position of the rock with respect to time would look like this. So it makes sense that this graph would be going up after we dropped it, because it's getting further and further and further and further away. So maybe we should have put a negative sign on there, but it's okay. We'll just keep it positive for now. Find the rate of change of the position of the rock with respect to time. So find S prime of 4 and explain the meaning of your answer. So we have this function right here, which is the equation for the position of the rock. And they want to know, what does S prime of 4 means? Well, that's going to be the velocity 4 seconds after we drop it. So if I do this, if our function was S of t is equal to 11.86 t squared, the derivative of that is simply going to be 2 times 11.86 which is 23.72 times t. So this equation now gives us the velocity of the object we dropped at every moment in time after we dropped it. And so if we want to find what S prime of 4 is, we simply just plug in a 4 right there. So let's do that. Let's multiply that by 4. And we get 94.88. So S prime of t is 94.88. So that's the answer. And what it means is 4 seconds after we dropped the object, its speed is 94.88. And let's look at what our units were. Let's go back up here. And we had seconds and meters. So that would be meters per second. So that's kind of cool. I mean, we're actually kind of learning, although this is simplified a little bit, we're actually learning the calculations that NASA does when they're trying to figure out how to get the trajectory of a probe to land on Mars or something like that, which is really exciting. So let's look. This is the position function. And let's look at the derivative function. This would be the velocity function. So The velocity function, you'll remember, was s of t equals 23.72t. And we're only looking at the positive part of the domain. And so we see that that's just a steep line. So let's connect these two. Let's see what's going on. This right here is getting steeper and steeper and steeper, because when you're falling, you're accelerating downward. You're getting faster and faster and faster as you're falling. So it's covering more and more ground faster and faster and faster. So it makes sense that its velocity function is just a constant growth function. It's just constantly getting up as these tangent lines get steeper and steeper and steeper. The slope of them is going up and up and up. So you see that we have a curved position function and a straight velocity function. By the way, well, let me not get too complicated yet. Let's look at this last example. The population of a city grows from initial size of 800,000 to size p given the following function, where t is in years. So we can see we've got a function that's approximating the population of a town. First, let's find the growth rate. Okay, so let's do that. Here's the population of our town, and we see that the growth rate is actually going to be independent of this 800,000 number. So we get p prime of t, or I guess they wrote dp dt. They both mean the same thing. And the derivative of this function, we can ignore that. And the derivative of this is 8,000 times 2, which is 16,000 t to the 1. So the derivative dp dt, which is the rate of change of the population, is 16,000 times the number of years that have passed. So find the population after 15 years. Well, if the rate of change, let's be careful here. This is the growth rate, but we want to find the population after 15 years. So that means we're not going to be plugging in 15 into this equation. We only want to be plugging it into this equation. So after 15 years, this would be the population. So let's find out what this number is. This would be 15 times 15 times 8,000 plus 800,000. So the population after 15 years would equal 2, 6, and then 5 zeros. So after 15 years, the population will have grown from 800,000 to 2.6 million people. So then in that case, what would the derivative be at that point? Okay, and so this is how many people there would be in 15 years. And if I plug in 15 into the derivative function, I would get 16,000 times 15. So I can see that that number is 240,000. So you need to know when to use the regular function and when to use the derivative function. So here they said this represents the population of the city. So if they ask how many people are there in 15 years, that population is just going to be this number right here. However, if we wanted to know the approximate rate of change at that 15th year, we see that that answer is 240,000. So in other words, this is the gain per year at the 15th year. So this is how much we gained in the 15th year, the instantaneous rate of change, whereas this is the population at the 15 year. So remember, derivatives are rates of change, and our parent functions, our starting functions, are what the actual amount will be. So hopefully these applications make sense to you. You can see that we're going to be able to use this in business and with some economic decisions, because if we're looking at the rate of growth or trends in the market, we'll be able to make functions to approximate those trends. And then we'll be able to answer questions like, excuse me, how many people should I hire to maximize my profits? Or based on the forecast of what people are buying or the population of a city, where should I locate? Or how soon should we locate? Or how many locations should we make? Calculus can help us get not just approximate answers to these questions, but exact answers, because that's what we're doing with the derivative. So hopefully all of this made sense, and we're going to learn some new derivative rules that's going to make this even more powerful in the next section. So I will see you there.